how we could convert transfer functions into state space representation. And we did that, completed it, and did an example. And of course, you got other solved examples in your notes. So today we are going to do the reverse, which is to convert from state space to transfer function. And so allow me to share my notes so that we can begin. All right. I thought I had it. Looks like I have to. Okay, just give me a minute, please. There you go. All right. So our discussions previously have been on how we can convert a transfer function into state space representation. Remember, we said that the reason why we need to convert to state space is because the state space representation is a representation that is understood by most digital systems. So the way we enter or design our feedback control systems and the way we put them into digital systems, whether they're computers or software tools, is through a state space representation. But it is very difficult for human beings to actually understand the relationship between the input and the output of a system, of a control system, by looking at the state space representation. We humans quickly understand the relationship between the input and the output of a control system when we look at the transfer function. It's much easier for us to interpret transfer functions than to interpret matrices or state space representation for that matter. So usually it is also important for us to be able to convert from state space back to transfer function. Then we can quickly sort of understand what goes on in the control system. So today that's what we are going to do. See how we can convert a system from its state space representation to the transfer function. Now, again, you have this set of notes. So what I'll do is I'll just quickly rush through it and give you examples that don't exist in your notes, and then we move on to something else. Okay, so typically we have seen that in all the state space representation, like if you have state space representation, for those who are joining us for the first time, is that we have to represent a system with state equations. So you must have some state equations, and then you must have an output equation. We have also agreed on the general representation, and that has been, and please remember all these matrices and vectors. The lowercase are vectors, the uppercase are matrices. So that this has been the representation in state space. Okay, we've agreed in general that state space representation needs to be in this form. Now, how then are we able to transfer or be able to convert this format into, how can we convert it into a transfer function? How can we convert it into a transfer function? And so that has been an easy process. All you have to do, the beauty with this is we can generate a formula. We can quickly generate a formula that is going to help us convert any state space representation into transfer function. Okay? And the way to go about that is such that you are required to do, you take Laplace transforms of the state space representation. And when we're taking Laplace transforms here, because we don't know the initial conditions of the system, we usually just assume that the initial conditions are zero. So we always assume that we have zero initial conditions. Zero initial conditions. Okay. So if we take the Laplace transforms of our equation of our two equations here, of course, this is a derivative. So we take the Laplace transform on the left-hand side and on the right-hand side. That makes it easy because then it becomes x s of s. Remember, taking Laplace transforms, meaning we are switching from time domain to a frequency domain. Of course, the right-hand side will be a x of s. Now it's capital because now we are taking Laplace transforms. And of course, b u of s. The second one is just y of s equals to c x of s plus d u of s. We've just taken the Laplace transforms of our state space representations. Now, it's easy to see from this that we can, let me call this 2a and 2b, okay? So that I can refer to each of these equations. So you can easily see that we can take 2a because there's x of s on the left-hand side and there's x of s on the right-hand side. So we can actually bring x of s to the left-hand side so that we have all x of s like terms on the left-hand side, and then the rest of the terms on the right-hand side. Now, I think by now we understand this. In matrices or in matrix manipulations, we don't do arithmetic manipulations of matrices. So we don't say x is equals to y plus b, and then we say x minus y equals to b. This doesn't work with matrices. If you're moving a matrix from one side of the equation to the other, you get its inverse. You don't subtract or add, okay? You get its inverse. So what that means is if I were to take this x of s, and of course I'm taking the whole term ax of s to the other side, then we have to get the inverse. So usually for matrix manipulation, this becomes, and I want to make x of s the subject of the formula. Now I know typically you think that this should be s minus a x of s. Typically we would do that, okay? But because the term s is complex, we do not just subtract it, we get its inverse. So you multiply it by an identity matrix. So if I'm to bring this, let me do this again, nice and slow. If we were to take this on the left-hand side, we would just say, if we are doing the normal, we would say s minus a x of s equals to b u of s. But the term s has to be in a matrix form. It cannot be in, it's not a scalar quantity. This has to be a matrix form. We must represent it as a matrix. If we leave it as s, remember this term, let me put it nicely because again, it's a small s. Remember, it's a small s because you're getting the Laplace transform of a derivative. So it is a small s. But because we have all these terms, all the terms that we have in our equations 2a and 2b are matrices now because we've converted them to Laplace transforms. They are all matrices now. So we are having a matrix multiplied by a small scalar quantity. So the only way to make, because we can't say, ladies and gentlemen, that you have 3 times 1, 0, 0, 1. We cannot do a manipulation of this. To do this manipulation properly, you have to make this into a matrix. The only way to make it into a matrix is to multiply it by an identity matrix. And that identity matrix, the dimensions will depend on the dimensions of the matrix you're multiplying it with. In this case, it's a 2 by 2. So we have to multiply this by an identity matrix, which again, we must know, which is 1, 0, 1, 0, 0, 1. So that it now becomes 3, 0, 0, 3. See? So it becomes this term. So that's why this term here must be multiplied by an identity matrix. Okay, I hope that's clear. So let me wrap this off. So remember, to manipulate matrices, you cannot just multiply them with scalar quantities like that. You have to sort of make them into a matrix, and the only way to do that is to multiply them with an identity matrix. So our clean question here, I might not have written it properly, is now Si minus A. So now this is actually a matrix. Si is now a matrix and A is a matrix, because now you can subtract them. You can subtract them easily. Okay, so now what I'm going to have here is, if you make x of s the subject of the formula again, it would mean that I have 1 over Si minus A B U of S. And this is what we refer to as Si minus A inverse, because we can get the inverse of a matrix, Bu of S, to be equal to x of S. Remember, I is your identity matrix. Identity matrix. So now we have x of S. Then let's come to question 2b and substitute for this value x of S in 2b. Remember, we are looking for the formula that we can use to convert a state space represented system into a transfer function. So from question 2b, we'll have y of S equals to C multiplied by x of S, and x of S is here. X of S is here, meaning the whole term is going to be multiplied by Si minus A inverse Bu of S. Okay, so that is x of S plus Du of S. Okay, so we are multiplying. Remember, the idea is, we know that y of S is usually the output, because for transfer function, you want a function that relates the input and the output. And from our definitions, we know that U of S is our input. So that is why we are looking for a function that is relating y of S and U of S. So we already have y of S on the left-hand side. You can see that this is the input, U of S, so that we have y of S over U of S. So clearly you can see that if we can just write this as, if we bring U of S on this side, you have your equation, which we are going to use throughout our manipulations. Is going to be, we have to multiply, let me see, C multiplied by this of B. Remember, if we were to bring this side, it means we had to factor out U of S for both sides. So that means this one had to be here for those who might be struggling. If I was to multiply out, I would be having C into Si minus A B plus D, and all of this multiplied by U of S, because there's a term here of U of S and a term here of U of S. So I have to factor out the common term, and if I do that, this is what I get. And so if I get Y of S over U of S, again, I feel like I need to write this properly. So let me make this Y of S. So now I move step by step. So Y of S over U of S, therefore, becomes C into Si minus A inverse B plus D. So this is what we refer to as our transfer function. This is our transfer function. So typically, whenever you are given some state space representation, remember, state space representation will consist of the matrix A, B, this is the state matrix, you've got the input matrix, you've got the output matrix, and then of course D, sometimes it's there, sometimes the transformation matrix is there, or sometimes it's not there. So you'll be given A, B, C, and sometimes D. And once you're given those, you can simply use this formula because you've got everything you need, so as to get the relationship between the input and the output in form of a transfer function, So that's all you need to know. Now, in your notes, you have an example. Remember, sometimes the questions that you're given could be either 2x2 matrix, a 3x3 matrix. So in fact, the idea here is usually to know how to obtain the inverse, because you can see that there's always an inverse. So if you have a 3x3 matrix, you must know how to obtain the inverse of a 3x3 matrix. If you have a 2x2 matrix, it's even easier. But of course, it can even be 4x4, but that usually is a more difficult inverse to obtain. So we'll restrict ourselves to 2x2 and 3x3. Okay. So again, you've got worked out examples in your notes. I expect you to read out and understand those. What I'll do is I'll solve one that exists in a previous past paper. I'm looking for that. Okay. Example. This is just for illustration purposes. This was in some exam. Convert the state and output equations. The state and output equations below to a transfer function. So basically, this will always be provided. So the state equation is already provided here as 0, 1, minus 9, 7. Plus. So that's the state equation. And the output equation is given by okay. So you are supposed to convert this. You can actually see that if you're given this form and I ask you for if you understand how this control system works, it would be difficult because you have a bunch of matrices and you have state vectors, but it's very difficult to know the relationship between the input and the output of a system by just looking at these state and output equations. However, when we convert this to transfer function, you can quickly understand what the system is because you can quickly see the poles, you can quickly see the zeros, you can know whether the system is stable or not, you can quickly sketch a root locus and all that. So you can understand the control system easier or more easily if the system is represented in a transfer function format. Okay. So again, remember that given this, you just need to use the formula for the conversion. So the formula, remember, is y of s, u of s should be equal to c si minus a inverse b plus d. That's the formula. So you all have to know what A is, what B is, what C is. And we have done this before. We have defined this before. This is A, this is B, AX plus B, and this is C. And of course, usually there's a plus D here, plus D. Okay? So you can know. So from here, you can tell that A equals to 0, 1 minus 9, 7. B equals to 0, 1. C equals to 1, 2, and D is 0, okay? Because we don't have it there. So then now we move on to substituting this into our equation. Now you have to do this step by step. And again, you have to remember how to do matrix manipulations. Are you moving from left to right or right to left? Very, very important. However, I will give you simplest way is to first solve this middle part, and because it's the most complex one. Once you have it, then the rest are just easy. So just solving this middle part is the key. That means let's first obtain what is Si minus A. Then we get its inverse. So Si minus A would mean, because we're dealing with a 2 by 2 matrix, we are going to have S0, 0S. Remember, this I have obtained from S into 1, 0, 0, 1. And so this is what we are referring to as Si. Okay, that's what I'm saying. That's why I have it as S0, 0S. Then we have to subtract A, and A is 0, 1, minus 9, 7. Okay, again here, you're most likely going to make mistakes in just the simple manipulations. So you have to be very, very careful with your arithmetics. You are just addition, subtraction, multiplication. That is what can flow you, because you make mistake in one element, the rest becomes wrong. You can't obtain the right inverse if you've got one element wrong. So you have to counter check every time. You have to make sure you subtract properly. So here you'll have S, you'll have minus 1, you'll have 9, and then S minus this should be S minus 7. So here you have S minus 7. Okay, so I hope that's clear. I can rub this off because I've shown you what that is. And now we want to obtain its inverse. So what is the inverse of this matrix? The inverse of this matrix would therefore be getting, and again, here you can use all the skills you've learned before in maths to obtain the inverse of your matrix. I know there are so many formulas you can use. There are so many methods that are available that you can use. As long as you get the right one, I don't have a problem. For a 2 by 2 matrix, I know the easiest one is to get 1 over determinant. Then I interchange the elements in the lagging diagonal. So I think I should have S minus 7, and I have S. Change the signs here, minus 9, and I change this to 1. I can't teach you how to obtain the inverse of a matrix. That's not really my work right now. And then, of course, you have to get the determinant. The determinant of this matrix of S minus 1, 9, S minus 7. The determinant should be, I think, S into S minus 7, subtract minus 9. So that will be S squared minus 7S plus 9. Okay, so now this was just a side math. Okay, so now I'll have here I minus A inverse should be 1 over S squared minus 7S plus 9 into S minus 7, 1 minus 9S. Okay, and that is the first part. Remember, that is, I've just obtained this. Now I need to include all the other vectors or matrices where necessary. So now I come back. Y over S over U over S should be equal to C. And what is C? C is 1, 2. So I'll have 1, 2 multiplied by, so C is multiplied by the inverse matrix. So multiplied by 1 over S squared minus 7S plus 9 of of this matrix here, S minus 7, 1, minus 9, S, and then followed by, so B plus D. So B is what? B is 0, 1. So here we have 0, 1. Of course, plus 0, because D is 0. Okay. So what that therefore means is we have Y over S, U over S to be equal to, because this term is a constant, I can bring it down here, 1 over S squared minus 7S plus 9. Then I do manipulations of the rest. So now I can do manipulations of 1, 2 multiplied by S minus 7, 1 minus 9S, then multiplied by 0, 1. Again, remember the order in which you are required to do matrix manipulations. Is it from left to right or right to left? If you get that wrong, again, your entire solution will be wrong. I'm only doing the easy one, 2 by 2 matrix. You could be asked to manipulate a 3 by 3 matrix. So if I multiply these two, I'm going to have 1, 2 here, like that. This is a 2 by 2 by a 2 by 1. So I should have a 1 by 2. So I'm going to have this 0, 1. So this is going to be easy. 0, 1. So that's just going to be 1. That's 0. This is just going to be S, like that. And so if I multiply again these two, numerator, it's just going to be 1 plus 2S. It's just going to be 2S plus 1 over S squared minus 7S plus 9. This is now my Y over S, U over S. So clearly, this becomes the transfer function of the system that has been represented using state space representation. So here, from here, you can see clearly you can know the location of the zeros. Okay, you can know the location of the poles, and you can quickly interpret the performance of the system, at least a few transient performance or steady state performance, whichever, but at least you can tell the performance of the system by just looking at this transfer function. So this is how you convert from state space representation to transfer function. Basically, it's just using this formula here. Just using this formula. Once you have this formula, then you can be able to substitute for the values that are required, and then you just do your matrix and vector manipulations, and you will obtain your solution. So I again urge you to do as many examples as possible. Some are in your notes, some you will find in other books as you read them. I hope you guys are reading other books. You're not just relying on my notes. You can read books and try and solve those problems as they come. It's very, very important that you do that. Okay. The other thing that I want to do today is because I want to start with design tomorrow. So what I want to do today is to just indicate that there are other forms. Remember, there are other forms in which we can represent the control systems. We have forms that we are calling canonical forms. Okay? Meaning, let me just indicate here, you have this in your notes. I'll be focused on doing examples rather than giving you notes because you have them. We can say that state space representation state space representation can be illustrated in 3 main forms. Meaning, There are three different ways of state space representation. There are different ways in which you can represent state space representation. The first one is known as controllable canonical form. Please note that these forms do not take away on the structure, the basic way in which we represent state space, meaning state space representation is known to have state equations and output equation. The structure remains the same. You must always have a state equation and the output equation. However, there are three forms of representing these, and that's what I'm showing you here. There are three forms. The first one is the controllable canonical form. The other one is called observable canonical form. And the last method is known as the diagonal canonical So these are canonical forms. In fact, let me say here in three main canonical, because that's a keyword there. So if a control system is represented in state space, there are three styles or three techniques or three forms in which we can represent state space. We can represent them as controllable canonical forms, or observable canonical forms, or diagonal canonical forms. These forms still have the two main equations, the state equations and the output equations. They still have those. It's only that the way in, or this, the way in the form in which, or the style with which the system is written differs. And this is done just because they're different digital systems. And those digital systems accept inputs and outputs in different formats. So if they are accepting the different inputs and outputs in different formats, then we must be able to represent the state space into different canonical forms. So there are those forms that take controllable canonical forms. There are those systems that take observable, and others take the diagonal canonical forms. But they, at the end of the day, they are equivalent forms. It doesn't mean that it changes the representation of the system. The system is exactly the same, but the form in which it is represented is what changes, but it is exactly the same thing. Okay? It's more or less like saying, if we do Pythagoras theorem, for example, somebody would say, in Pythagoras theorem, we would say h squared equals to a squared plus, is it the adjacent and the, let me say, an o squared. But somebody would say h equals to a squared plus o squared square root. These people have said one and the same thing, but they have represented the system in different forms. Somebody can say a squared equals to h squared minus o squared. Again, we're still talking about the same system, but represented in a different form. That is exactly what we are saying with the state space representation, that the representation of the system does not change, but the form in which we represent that system. In fact, there are more forms. There's even one I've just remembered. There's another one called Jordan canonical form. If you read about them, in fact, most of them I think are discussed in that book by Katsuhiko Ogata, Jordan canonical form. Okay, so that is another form. All right. Now, not to surprise you, but the form that we have been using, the one that we have been using by saying AX plus BU, and then we say output equation is equal to CX plus DU. This is typically called the controllable canonical form. That is typically usually the controllable canonical form, meaning it is the form that we have been using as an example for state space representation. But we can still write this controllable canonical form in an observable canonical form, meaning it's going to be equivalent in structure but different in form, but the representation is still equivalent, meaning the interpretation that is going to be done by the digital system or when you're doing simulation is going to be exactly the same. It's only that some are taking the forms differently, but the representation remains the same. So you can be given a system, you can write it in controllable canonical form. You can also write it in observable canonical form. You can also write it in diagonal canonical form and write it in Jordan canonical form, meaning it's easy to translate from one form to another. You will read the rest in your notes. I want to give you an example that you don't have in your notes, okay? For example, let me now have to... So the idea is the different forms are illustrated in your notes, how you can write the different forms. But the best way for me to illustrate these points to you is to actually give you an example. So if you were asked, for example, that obtain, wait, that's not the right way. Say, consider the system, a control system, consider a control system given by y of s over u of s. Remember, you're given this form in a transfer function format, s plus 6 over s squared plus 5s plus 6. So you've been given a system in transfer function format. So the question is, obtain the state space representation. Obtain the state space representation in one, controllable canonical form. And 2, in observable canonical form. And in 3, in diagonal canonical form. Number 4, in Jordan canonical form. Good. So that is a typical question. You've been given a control system in transfer function format, but you've been asked to represent it in controllable canonical form, observable canonical form, diagonal canonical form, and Jordan canonical form. Remember, all these canonical forms are forms of state space representation. They are forms of state space representation. So if you read the question carefully, you will understand that 1, we first must convert the transfer function into state space representation. But I have just given you a hint previously here that the state space representation that we have been using all along is typically referred to as the controllable canonical form. It's the one whose example we have been using all along. Therefore, the question means here that if we are able to convert the transfer function into state space, then already we would have solved the first part of the question, because that state space representation that we have been using is actually the controllable canonical form. Then we can use other techniques to convert to the equivalent observable, diagonal, and Jordan canonical forms. That's what I intend to do. And then we end the class here because I have a meeting. Now, typically, you understand what to do when you are given a transfer function and asked to obtain the state space representation. The first thing you have to do is look at your transfer function. Because whenever, if you remember, those who have been attending previous classes, if you remember, there is always that caveat that before you start converting from transfer function to state space representation, you must look at the transfer function itself and note whether it is one of the two types that we talked about. Meaning, do we have a constant term in the numerator, or do we have a complex term in the numerator? If we have a complex term in the numerator, you know what to do. If we have a constant term in the numerator, you also know what to do. If you don't, refer to previous notes. In our case here, let's start by converting this to state space representation, which actually is the controllable canonical form, like I've told you. So if you look at our equation, our transfer function, you can see that the numerator is also complex, okay? And therefore, we go for the second method that we talked about in the previous class. And we said that for a complex numerator, what you have to do is to cascade the system such that the denominator forms the first block and the numerator forms the second block. What am I talking about? I'm talking about saying that if y of s, u of s equals to s plus 6 over s squared plus 5s plus 6, what we do is we say this is equivalent to, we cascade the system where, and that order is very important. The first block, remember the input is u of s and the output is y of s. The first block has to be the denominator term. So s squared plus 5s plus 6. The second block has got to be the numerator term, s plus 6. So we can put in, for easy reference, we need to assign a notation here. Let's call it, for example, we can use any term. Let's call it t of s. T of s. You know, such that we are saying, ladies and gentlemen, this is usually like saying y of s over u of s is the same as somebody saying, sorry, what am I doing? It's the same as saying t of s over u of s multiplied by y of s over t of s. So this is the first block. This is the transfer function of the second block. Because if you cross multiply, you'll see that this crosses out with this, and you remain with y of s over u of s, which is exactly what we are referring to. So it means we are just cascading. We are separating the system for convenience of manipulation, but we are still referring to exactly the same system. Nothing changes, okay? So now, again, remember the idea was we are converting this to state space representation. So we start with the first block. Remember we said that for cases where you have a complex term in the numerator, then you cascade the system like this, use the first block. This first block is used to give you the state equations. For those who have done this and done other examples, I've noticed that this block is used to give you the output equation. because state space representation must consist of state equations and output equation. So the first block is for state equations. The second block is for output equation. Use the first block to obtain the state equations. And that is very simple to do because we've done it before. So now it would mean the first block, its transfer function for the first block is T of S over U of S is given by 1 over S squared plus 5S plus 6. That we now know. Now, because our first block has a constant term, it is just 1 in the numerator, it's very easy to manipulate. Okay? How do we manipulate this? I gave you steps. The first step now in our case here is we cross multiply. Let me use the word cross multiply because last time I used the word linearize and it confused a few people. So I'll just say, let's cross multiply this term. If we cross multiply, we are going to have S squared plus 5S plus 6 of T of S should be equal to U of S. Just cross multiplying the terms. The second step after cross multiplying was to obtain the inverse Laplace transforms, of course, assuming 0 initial conditions. You have those steps in your books already. So I'm just going to convert this back to time domain from frequency domain. This is a double derivative, so I'll say 5S, that's a single derivative, so 5t plus 6t should be equal to U of t. Okay, or just U, it's no problem. Then what do we do next? We obtain state variables. Remember, we are converting a transfer function into state space representation, which we are calling controllable canonical form. Now, how do we know how many variables we pick? We look at the order of our differential equation. Our differential equation is second order, meaning we need 2 state variables, x1 and x2. Remember, the idea is to have a format where we have x equals to ax plus bu, and y, which is the output equation, is equals to cx plus du. This x is a vector actually. In fact, writing this in full, because sometimes people confuse, writing this in full means you write x1. If you have a second order equation, it means x1, x2, like that, equals to some matrix. Then you have x1, x2 as a vector, plus b, and then you have u, of course. I don't know what u is. And then y is a scalar quantity, is just going to be cx, meaning c, of course, you have to write it in terms of the state variables, x1, x2, of course, plus du. Again, I don't know how many inputs are there or whatever, but you can see that these are the state variables, x1, x2. That's why we are saying here, let our state variables be x1 and x2. If they were third order, then we would be saying x1, x2, and x3. Fourth order, x1, x2, x3, x4. Okay? But I hope you're clear on that by now. So our state variables are just x1 and x2. So let me get this off so it does not distract us. This is the format we are looking for. So we said, how do you assign state variables? You look at your differential equation, look for terms that have got their derivatives. So we pick our state variables as terms or those physical quantities that have got derivatives. So if you look at your differential equation here, it is t that has got derivatives, not u. U has no derivatives here. So we can't pick u as a state variable. But because t has derivatives, we typically pick them as state variables. So the first variable would be t, the second variable would be the derivative of t, single derivative, and then the third one would be a double derivative. If there's a fourth one, it would be a triple derivative, and so on and so forth. But in our case here, we only have two state variables. So the first one would be t, and then the second one would be the derivative of t, like that. Okay, so now remember, we are looking to write our equation such that on the left-hand side, for the state equation, for the left-hand side, we need to have x1 bar and x2, or the derivative of x1 and derivative of x2. That is why we do what is called, we differentiate, such that we can have on our left-hand side x1 derivative and x2 derivative. That's what we're looking to find. So now, if we differentiate the first one, x1, if we differentiate it, it means we have to differentiate the t. But the derivative of t, if you look at the second equation, is the same as x2. Now let's go back to differentiating the second one. If we differentiate x2, what do we get? We differentiate x2, we get double derivative because it's already differentiated on the right-hand side, so we have to differentiate it twice. So if we differentiate this twice, then you come back to the equation here, you find it here. So we make this the subject of the formula so that we can have it in forms of t, the derivative of t and u. So we could say that the derivative of t, which is this guy here, I mean the double derivative of t, which is this guy here, is the same as writing minus 5 derivative of t. I'm making derivative of t the subject of the formula. Minus 5 derivative of t minus 60 plus u. Okay? But this is the same as saying minus 5, because we don't need this in terms. Remember, the right-hand side is in terms of x, x1, x2. Those are the state variables. So you see, our right-hand side here is in terms of t. So we have to change those in terms of x. So we can say minus 5. What is the derivative of t in terms of x? I see the derivative of t here as x2. So I'll just write this as x2 minus 6. What is t in terms of x? I can see from here that t is just x1 plus u. Okay, so that clearly means now, you see now I have an equation where on the left-hand side, I have x1, x2. And on the right-hand side, I have the equations. So this is catered for. So on the right-hand side, you just need equations in terms of x and u. And that's what I also have on the right-hand side. So now we can actually solve this and say the state equation, therefore, state equation. I told you the first block is only for the state equation. So the state equation would be x1, x2, like that, to be equal to. Now we have to come back to the right-hand side and write it in matrix form. We have to look for the coefficients of x1 and coefficients of x2. Okay? Because you have an equation where you have x1 bar equals to x2 and x2 bar equals to, I can write it as minus 5x2 minus 6x1 plus u. So I can even write this properly so that I don't confuse you. I can write it as minus 6x1. So I start with x1 minus 6x1 minus 5x2 plus u. So let's write this in terms of a matrix, because you need a matrix here, you need a matrix here, then you need x1, x2, then we'll add the u's later. So what are the coefficients of x1? In the first equation, the coefficient of x1 is 0. In the second equation, the coefficient of x1 is, because it will be, the first equation, the coefficient of x1 is 0, the coefficient of x2 is 1. In the second equation, the coefficient of x1 is minus 6, the coefficient of x2 is minus 5. But we have the u, so the u does not exist in the first equation. So in the first equation, u is 0. In the second equation, u is 1. The coefficient is 1. So it's like that. So this becomes the state equation, and this is the controllable canonical form. For the first, just the state equation, because the controllable canonical form requires us to write also the second part. Now, if we go to the second part of our this is because remember, we've only done the first block that has given us the state equation. We have to do the second block to give us the output equation. Okay, the second block has to give us the output equation, and you can see that the second block should be y of s over t of s should be equal to s plus 6. Okay, let me write that down here. Y of s over t of s should be equal to s plus 6. So again, we cross multiply, and if we cross multiply, we'll find that s plus 6 t of s equals to y of s. And therefore, you can, again, let's write the inverse Laplace transform. This side would be y of t, okay? And this side would be s, that is a derivative of t, and 6t. So you have an equation where you have y equals to the derivative of t plus 6t, okay? And you had already known from here, you can see what are your state variables. The state variables must remain the same. They must remain as 2. If you look at this equation here, the differential equation we are dealing with in this case here, the differential equation here is first order. So I'll need x1. And that x1, I can pick it as the term that has a derivative, which is t. And therefore, x1 bar, notice I'm not getting x2 in this case, because our equation, our differential equation here is only of the first order. So I'm only picking one state variable in this case for the second block. If this was, if the differential equation was or of order 2, then I would pick 2 state variables. If it was of order 3, I would pick 3 state variables. You know, like we've done with the first block. So because in this case here, we only have one, the first order differential equation, we are picking only one state variable, x1 of t. And then of course we are differentiating like we did. The process remains the same. So if we differentiate, you get a derivative of t. But the derivative of t, clearly, you can see the derivative of t from our first block. Remember, derivative of t was what? Derivative of t is x2, okay? Because this is the same system, so we cannot run away. The state variables are similar. So derivative of t is x2. So therefore, we can say y itself, I can rewrite the equation and say y equals to derivative of t, which we know is x2, plus 6t, which is 6x1, because t is x1, 6x1. So therefore, the output equation becomes y equals to, because I need to write it in terms of something like that, x1, x2, because d is 0, okay? x1, x2. So what's the coefficient of x1 in this equation? It's 6. The coefficient of x1, I think, is 6. Let me make sure I'm correct. 6t. So it should be 6x1. 6x1. Good. So the coefficient of x1 is 6, and the coefficient of x2 is 1. Yeah? Coefficient of x2 is 1. So, ladies and gentlemen, this plus what I have written here as y equals to 6(1), x1, x2 is the controllable canonical form. This term here, these two equations, is the controllable canonical form. This is the controllable canonical form. Okay? So remember, we have just solved the first part of the equation, the controllable canonical form. 3 more to go. Okay? Oh, my meeting is about to start. Anyway, let me go on. So, second part, let us solve the second part, which is observable canonical form. Now, how do you obtain the observable canonical form? It's very simple. There are only 2 steps in obtaining observable canonical form. And remember, the observable canonical form is obtained from the controllable canonical form. So you must always first get the controllable canonical form for you to obtain the equivalent observable canonical form. So what is the formula or the steps for obtaining the observable canonical form? Step 1, you have to transpose the n by n state matrix of the state equation. And then step number 2, very simple steps. You have to interchange the input matrix. That's why you have to know these matrices. You have to interchange the input matrix elements, that is the elements of the input matrix elements of the state equation with, what do you interchange them with? You interchange them with the output, matrix elements. Of the output equation. It's a mouthful, but the interpretation is very simple. Let me rewrite the controllable canonical form down here so that it's easy for us. The matrix is 0, 1, minus 6, 5. So we know that the controllable form is this form. Is x1, x2 should be equal to, it is 0, 1, minus 6, 5. This is the controllable canonical form. The plus, is it 0, 1? Yeah, it is 0, 1. And the second one, the output equation, I think it's 6, 1, or is it 1, 6? 6, 1. The output equation is like that. Okay? Now, this is controllable canonical form. Don't forget that. But now, to convert this to observable, we are told, number 1, we have to transpose the n by n state matrix of the state equation. Yes? Sorry? Oh, it's minus 6, minus 5. Oh, yeah, thank you. It's minus 6, minus 5. Okay. I forgot to put that there. It's minus 6, minus 5. Thank you. So now we are supposed to, 1, transpose the n by n state matrix of the state equation. Okay. Now, I want to believe that we know how to get the transpose of a matrix. So step number 1, we need to transpose this matrix here, the state matrix. So it means that we have to transpose this matrix here. And then number 2, we have to interchange the input matrix elements The input matrix is this one. In this case, it's a vector. Okay? We have to interchange them with the elements of the output matrix. So we interchange them with this matrix here. That is how we obtain the observable canonical form. Now, take the journey with me. Let me show you how to do it. Let us first do step one. So step one, let's transpose. So if we transpose, it means we are only transposing. For the transposition, we are only doing it for the state equation, meaning we are only doing it for this. This is our state equation. This is the state equation. Or not state equation, state matrix. Sorry, state matrix. My mind is already in the meeting. Let me finish this very fast. So this is a state matrix. This is the input matrix, or vector if you want to call it. And then this is the output vector in this case. Okay. So now let's begin by the transposition. So if we do the transposition, we are going to have, remember, we are only transposing. This has to remain the same. The left-hand side remains the same because it's still state space representation, but the form in which we are writing it is changing. So if we transpose this matrix, I want to believe everybody in this class knows how to transpose the matrix. I think this was 0 what? 0 1, eh? 0 1. And let me just make sure I don't write my own things. Yeah, 0 1 minus 6 5. Okay. So transpose the matrix. We are going to have 0. I hope that's the correct transposition. Then you have x1, x2, like that, plus 0 1 u. Okay, that's step number 1. It's not yet done. So step number 2 is we are now to interchange the elements of the input matrix with the elements of the output matrix, meaning this matrix or vector here that is the coefficient of u is brought to be the output, and the elements of the output here should come to the input. So when we do step number 2, we should have, so this is step number 2, x1, x2 now should be equal to, of course, 0 minus 6. We have transposed that already, like that, x1, x2, plus. Now it is not 0 1. We take the elements that exist here. The elements of the output matrix is 6 1, and we give them to the input. Okay, u of t. And then the output y should be equal to, now the output is not 6 1. We take the input matrix 0 1, 0 1, and we put it there as the coefficients of the state vector, like that. So this becomes the observable canonical form. Meaning, to get the observable canonical form, we must first get the controllable canonical form. Once we have the controllable canonical form, there are 2 steps to take us to observable canonical form. The first step is to transpose the elements of the state matrix. Once you transpose those elements, then you interchange the input matrix with the output matrix, or the input vector with the output vector. So you take these elements, you bring them here, and you take these elements of the output vector and you make them the input. So it's like taking what exists at the input, you put at the output, and what exists at the output, you take to the input. You're interchanging the input with the output. That is what you do to get observable canonical form. So this is now what we are referring to as the observable canonical form. Remember, it is still state space representation. The terms on the left-hand side still remain the same. The form in which we write the right-hand side is what is changing. Okay, good. The other one was to do what? To write it in diagonal canonical form. Diagonal canonical form. So how do we get to diagonal canonical form? Again, pay attention. Diagonal. This is now number 3. The diagonal canonical form. Remember, all these are just forms of writing state space representation. Now, in diagonal canonical form, the procedure is a little different. Okay? In diagonal canonical form, we do not obtain diagonal canonical form from observable canonical form. Neither do we obtain it from controllable canonical form. In diagonal canonical form, we have to go back. We have to go back all the way to the transfer function. And this is the transfer function. So let me show you how to obtain it right from the transfer function. From diagonal canonical form, we have to write the transfer function afresh. Y of s over u of s should be equal to s plus 6 over s squared plus 5s plus 6. What do we do next? We have to factorize the denominator, meaning it's like we want to obtain the poles. We have to write it in terms of the poles, okay? So this is like saying s plus 6 over a number. If you multiply, you get 6. If you add, you get 5. That is 2 and 3, yes. So this is s plus 2, s plus 3. So notice I'm writing it in this form, ladies and gentlemen, so that you have s plus the first pole and s plus the second pole, s plus p2. Okay? That's the format in which I'm writing. Why? Because in general, and this exists in your notes, that's why you have to read your notes also before you start solving these problems. In general, for a 2 by 2 matrix, or for a second order, you can see this is second order. You have examples of third order also in your notes, but for a second order, x1, x2, this is like a state equation, remember, should be equal to, this is in general how we write it, 0 minus p2. Remember, this is like writing the state equation, x1, x2, plus 1, 1, ut. This is the general representation. Y should be c1, c2, x1, x2. So this is the general format for diagonal canonical form. The general format. You can see that in the general format, we must write the state equation in this form, where you have the negative of the first pole, the negative of the second pole. So poles are listed in the diagonal, in the leading diagonal. If there were 3, then we would be having another third one, okay? If there were 3, you'd be having something like this, x1, x2, x3. That is if it was a third order, okay? We would be having something like this. Minus p1, 0, 0, 0, minus p2, 0. Then everything else, all the other elements have to be 0, 0, 0, minus p3. So these are 0, 0. So you can see it's minus p1, minus p2, minus p3. And then, of course, you'll be having x1, x2, x3. And then notice that the input matrix is 1. It's unity, meaning at the input, you supply only a unity value. So then the output matrix would be C1, C2, C3. See, it's a general form that you have to know. And if it's fourth order, it goes on in that manner. But only that in our case, we are dealing with second order. So this third order is not applicable. So I'm going to wrap it off. But you can do as many orders as possible, and the formula is in your notes. So shouldn't be a problem obtaining that. Okay. In our case here, it's just second order. So allow me to just proceed with the one we have and obtain the diagonal canonical form. So now, this is the general format in which we write the diagonal canonical form. But we've seen we can easily now get P1 and P2 because you simply factorize your denominator term so that you get your poles. But now, how do you obtain C1 and C2? Okay, so let's do the first part, because meaning the state equation. The state equation, then we'll see how we get the output equation. So in our case, the state equation is easy now, because once you factorize the denominator, the state equation would be x1, x2. Notice the left-hand side is always the same. That is why the state space representation doesn't change. It's the form or the format that changes. So we need to have a matrix here. So what is the minus P1? The first pole is 2. So the first pole here could be minus 2. The rest of the elements would be 0. The second pole is 3. So it's minus 3 there. Okay. Let me see that. And then we have x1, x2. The input is always 1. So you see the input is just 1. That doesn't change no matter what the system that you're given. The input is always 1. So that is how you write the state equation. But now, how do we get C1 and C2? The equation of output method C. Good. That is not difficult because we know that our transfer function, remember, our transfer function is s plus 6 over s squared plus 5s plus 6. So we can write this in the form of, so notice that here we were factorizing the denominator so that we get the state matrix P1, P2. Then now we have to factorize the numerator for the output matrix. So for the output, for us to obtain the C1 and C2 for this output vector or output matrix, we would have C1 over S plus 2, okay, plus C2 over S plus 3. That's how we write it in that form. Again, if you've done manipulations before for differential equations or just for matrix, for differential equation, when you solved, I think this was in not numerical methods. I don't remember, but there was a topic on differential equations where you can solve them in this format. So notice it is the numerator term that we are splitting. So we are splitting the numerator terms into C1 and C2. If we had another third pole or another third factor in the denominator, we would go on, and so on and so forth. Okay. But in our case here, we only have 2 of them. So you factorize them like that. So then again, if I ask you to obtain C1 and C2, can it be difficult? In this case, it's very easy to obtain for me C1 and C2 because solving this, one of the easiest things you can do now, I want to believe we can solve it. You would not expect me to solve this for you. It's very simple. Least common multiples and so on. Solve for C1 and C2. You've done this before. We've done this where you factorize these terms. Please do that. I am already late for a meeting, so solve this, obtain your C1. Yes, 4, 2 is minus 3. Okay. Once you obtain that, then you can write your output equation because it's C1, C2. So it will just be 4 minus 3 of x1, x2. So that now the diagonal canonical form consists of this part and this part. Okay, that forms the diagonal canonical form. The third one, the fourth one is the Jordan canonical form. Ladies and gentlemen, I'm forced to leave this as an exercise for you. Please go and solve it and obtain the solution because I am already 20 minutes late. So I want to end here unless there's a very specific or burning question that you'd want to ask me. Please allow me to stop here, solve the problems that exist in your notes, look for other problems. Again, this has been solved extensively in the book Katsuhiko Ogata, Control Systems. Please have a look at some of the worked out examples there and see how many you can solve. That being said, I beg to end my class here today. We proceed tomorrow. Is there any question?
Yeah, excuse.
Yes, Ogola.
I wanted to ask about the poles because there you've indicated that the first pole and the second pole is -3, but if you manipulate the denominator, you find you've indicated that they're positive, of which you've just negated to get negative, but when you manipulate the denominator, you find that negative. So negative P1 will be positive. So I don't know how you've gone through it.
No, it's like saying, you see, this is a general format for writing this. Okay, that's how it has to be. But now you have to obtain. You see, Gola, this is maybe I think you're asking a very pertinent question. Let me see how I can help you with that. You see, if we solved for this pole here, if we solve for this pole, what are we going to obtain? We're going to obtain S equals to minus P1. And then we are going to obtain the second pole as S equals to minus P2. So those are the exact locations of the poles. Those are the ones you list here. So for example, let's say you had S minus 2 and S plus 4, okay? It means we are going to have the first pole as S equals to 2 and S equals to minus 4. So these two change into 2. Notice these two change into 2 and minus 4. So the reason why they are negative here is because the assumption here, the assumption we made up here was that we have S plus P1, S plus P2. So the only way to quickly understand this so that you don't confuse yourself is when you find the exact location of the pole. That is what you list down here. So this is actually the exact location of the pole. So if you had S minus 2, then the pole is at position 2. So that's what you list here. If you had S plus 4, then the pole location is at minus 4. That is what you indicate here. I hope that's clear.
It's okay, thank you.
Exactly. So the exact location of the poles is what we list down in this state matrix. The exact location, not the negative of the location. The reason why it is negative here is because we have already assumed that we are having S plus P1, S plus P2, S plus, but you can also have S minus. So the only way to know it certainly is just solve for the exact location of the pole, and that is what you list down in this order, in that order. Now again, remember, and because somebody might ask, why not S plus 3 and S plus 2? Why S plus 2, S plus 3? Why not S plus 3, S plus 2? Such that we now have here, we have minus 3 and we have here minus 2. Again, that is still allowed. There's no problem. It doesn't change anything. So the elements in the diagonal can keep changing based on how you've listed your poles. We are not listing them in order of magnitude. Okay. So if somebody had S plus 2, then S plus 3 first before S plus 2, then they would be having minus 3 here, and then they'll be having minus 2 here. It's still the same if somebody wrote here minus 2, minus 3. What we mean is as long as in your state matrix, the leading diagonal consists of all the locations of the poles, then we are fine. That's what we want. We want the leading diagonal of the state matrix to consist. That's why it's called diagonal canonical form. So somebody observing diagonal canonical form can see that the leading diagonal of the state matrix contains the locations of all the poles of your system. That is what it means. So that is what is expected of you. Okay? Kuna swali lingine tena? Please ask before I stop sharing again. Anyone else ask before I stop sharing? Good. Silence means we are good to go. Thank you very much. We'll proceed with our class tomorrow, where we now look at the design of control systems. I've shared the notes with your class reps already. You can start reading ahead of me. And because I want us to finish, if we don't finish tomorrow, then we'll finish our classes on Monday. Then the rest of the time will be just for revision. Thank you very much. Have a good day. Goodbye.